Hello, everyone. This is Hilary Chang. In our research, we quantify the uncertainties of earthquake source parameters related to local site effect using a dense array in Oklahoma. The name of the array is LASSO, and this is the map view of the array. It spans across a 25 to 36 kilometers regions. And in these small regions, we have 829 stations and more than 962 events that is associated with local wastewater injections. So this high station density and the catalog provide us a good opportunity to investigate the influence of local site effect on this source parameter estimation. Here is an introduction of how we characterize the earthquake source. We are interested in three parameters: the Cochran frequencies, the FC, which is the where this spectrum start to turn the shoulder of this earthquake spectrum. The second one is the seismic moment, the M0, which is related to the low frequency plateaus. So we fit the functions to get these two parameters, and we use the Cochran frequency and the seismic moment to calculate the stress drop. A previous research investigate the local seismicity, and they find out that the Cochran frequency and the seismic moment they get, they vary across the array. They show these spatial patterns. This can be due to the focal mechanisms, or it can be due to the side effect. So in this study, we quantify how much the side effect contribute to these spatial variations. You can see the variations ranges from positive 25% to negative 25%. So it's quite large. We use the PGV, the peak ground velocity, to quantify the side effect. And here, the map here shows the average PGV value we get from 14 regional events. The high PGV side corresponds to the young alluvial sediment, which is the map I overlay on top of. And this young alluvial sediment, they are soft, so they are supposed to have larger side amplifications. Other proxies we have tried include the rooming square amplitude, and this shows a very similar patterns to the PGV, and also the topographic slope. But this is not a good place to test these parameters because this region is rather flat, so most of them are noise. And also we try to use a simple template to do a template matching to get the P arrival delay, but the result is not good because the waveform changes between subregions. So we need a more sophisticated approach to get the shallow velocity variations. In this research, we focus on using PGV as our proxy of side effect. We correct the source parameters empirically using PGV. So we plot the Cochran frequencies, the seismic moment, and the stress drop against the PGV. And this is one event. So these dots, they are station measurements. As you can see, we have lots of stations for one event. And the Cochran frequency, it shows a negative correlation with PGV, whereas the seismic moment, it shows a positive correlations. We remove this trend using regressions and recalculate the stress drop. We do that for all of our 962 events. So each dot here is one event, and there are 962 of them. We find out that the spatial standard deviation decreases after correction. This is the deviation before and after correction. So after correction, all the values, in general, they shifted below this one-to-one line. And on average, the log-10 Cochran frequency values, its spatial deviation decreases by 18%. For seismic moment, it decreases by 12%. And for the stress drop, it decreases by 8%. So using that dense array, we are able to estimate how much this side effect contribute to the variations in those source parameters. So please see our posters number 190 for more details. Thank you very much.